Yes. Let's check out some data set. We did this last week, but I wasn't clear. I fumbled a bit. Let's see. Oh boy. Let's create a new one. So our task, we already went through a convolution and we already understand that it is important in image processing in order to uh, use image in a neural network, right? We have image that contains some object in there. It's either dog, cat, bird, and all of those things. We have the what is it? The dense layer at the end in order to detect to do classification. So this is the input layer and this is the output layer. So let's just make some random shape. And this is fully connected. It's fully connected, which means every node here connect to every other node from the input, but those are fine because in between we use convolution. We use a bunch of kernels to extract a bunch of features, images, and in after that we extract it again and again until at the end when we extract enough, the features image is small enough, we don't really care about the localization, we don't really care the position or anything anymore. Or in other words, the features at the end, it's become high level enough that we don't really care about the position. Well, let me check if it is quoting. If it is high enough that we don't care about the position, we can flatten them out into a single vector, a list of number, and then we apply it to a normal dense layer as we did before. So this is a dense layer or fully connected layer, whichever one you want to call it. At the end, uh, the last layer is the output layer, which usually contain a limited sets of number or a vector with a certain size. So let's say we're trying to predict the number in the image, right? Between see the 0 to 9, so any of this digit, at the end we would have a vector with the size of 10. Each of those represent a logits, or if we apply softmax, it's represent a probability distribution. All of them add up to 1. So it would look something like this sometime, if it's good enough that it can predict a certain thing very confidently rather than a bunch of noise. So this is what we have, right? We have a feature extraction in between, and then we have one more feature extraction, but this time it is classifying the features from the input, which number it is. So that is what we have so far. Now, our concern right now is um, in the domain of facial recognition, face recognition. And it's not only applied to face recognition, it could be a lot of other things. Adi did his research with the school on what is it, defect detection, whether an image contain bad part of a engine or something. So you take a picture of engine and see if it bad or something like that. So the reason we want to touch on this is because it is very important, right? Um, it's introduced a new idea, very very old idea, but it helped us look into neural network a little a little bit differently. So let's say the number of class at the end is unknown, right? So we have image of Bob here, and we have, hold on, Bob. We have image of Alice. Let's say we only have two image for now. So if it is just two, and if the end result is known, which means we know there's going to be Bob or Alice. There's not going to be anybody else. Or there could be the third one that is unknown. So we don't really care who it is, but it is unknown. That is fine. That is totally fine using our current architecture. The reason is because you can just set the output to um, three-dimensional vector, and each of those tell the logics of each of this in the picture, whether how many percent, how much is it, how much Bob is in the image, and so on. But what if we don't just want to train it on this two guy? What if the image, the person inside the image, could be me and you or somebody else? You know, like when you use your phone, you take a picture of yourself to do facial recognition. So the phone doesn't assume 7 billion people on this planet. They're just gonna wait, and then when you take your picture, it learn about your face, and then when you unlock your phone, it will look at your face and see whether the face is matching with the current one, the one that it already understand, right? And see if a different face is matching or not. So it is a problem that is in the form of following. You have all of this face that is available, but the number of face can be extended. You don't really know how many faces are going to be there. And we cannot use a um, fixed output classes anymore. We cannot have a predetermined number of class at the end. I need you to get this part. We cannot have a fixed number of class at the end anymore at this point. All right, let's take that in. Let me check anybody in. No. So if we cannot do that, how are we gonna solve this problem? This is where embedding come into play. And embedding is just a fancy word. It's basically the thing we've already been doing so far already. And if we use a dense layer, each of those layers is an embedding. So what does it mean exactly? Let's just get through it. So instead of using a fixed number of output that depends on the number of class, so let's say 10 or 2 or 3, let's just put it to some number that could be changed later. It doesn't really matter. So usually we put it to a high enough number, but not too low or not too high. So let's say even 64 is fine, right? So this vector at the end will now have a 64 component. Or sometimes you use 128. Those doesn't really matter. Sometimes you use a smaller number, 32. The power of 2 is just a good rule of thumb, so that not this number can fit into memory properly, rather than being left out and so on. There's a lot of problem with that. But any of this number is fine, right? Just not too small, not too large. Most of the time in larger network we use 256, a lot more. So let's not worry about that. This number could be anything. What's important is that a vector is essentially a point in space. This is what we're trying to get at. A 2D vector. So if the vector is two component, right? It's just a point x and y. So x, you have x and y in a two-dimensional space, whatever that space look. And two-dimensional space is easy to visualize, but 64 dimension is impossible. Our brain it's not able to comprehend that space. But the point is, this vector or this vector is a point somewhere in this space, no matter what. So that is what we call vector space at this stage. A space is just fancy word, but we like to use it. A vector space, a point, a space that contains point. So that's it. And this is a vector space on its own. This is a point in a vector space. Now, the metric multiplication that we have here, the dense layer, right? From this space over here. So this is a space on its own. So let's say this thing over here is 256 or whatever number it is coming from the dense layer, from the feature extraction, is a space on its own that is different space from this space over here. So it is another space, right? And it is a space that represents low-level ideas because we're extracting stuff from here, become from low-level extraction to high-level extraction here. But when it gets to this, it's still, in a way, a lower. I might get a bit too much noise in here, but a lower abstraction than this space. So this space has higher level of abstraction. And the reason it's just convenience for the network to learn. So this matrix multiplication, as we learned last time, is a transformation. So if you multiply a matrix with a vector, it transforms this vector from this space into a new space that we have here. So this is the output vector, right? So it's just a way of transforming one point from one space to another space. But if you put a bunch of points and you let it learn the matrix the way we have here, at the end, point that has similar meaning, if it need to be, will stay close together. And those are enforced by the loss function at the end. So if you compare the embedding or the logics, just like before from the dog and cats, for example, if you apply a loss function, right, the model will learn that a point that corresponds to a picture of a dog will stay close together, so that when it does classification, hold on, let's plot them out, and a point of cats, for example, and the nature of classification is that there is a division in between, so that if a point is beyond a region, the output is classified to be a certain class, and if it is beyond another region, it is classified to be a different class. The model learned to push all of those points closer together if they are closer in meaning. Alright, so that is embedding space. So embedding basically means a space that has similar point, has similar meaning, stay close together. This is a bit nitty-gritty into the details of mathematics. You don't usually really need to know this, but it leads us to solve the facial recognition. So all of this space doesn't become embedding space on its own. The reason it's become an embedding space is because the nature of loss function. So in order to identify if something is a dog, we look at the highest and we take out the argument, the class, the index, whichever it is, and we assume that that is the output, and the loss function literally doing that, and it going through all the data set for each point doing that, so that the transformation, when it learned to extract those points from this space to this space in such a way that the point that has similar meaning stay close together for your classification algorithm or for your loss function. It's just trying its best to satisfy the loss function, right? So that's what's happening. I might get a bit too far, but the point is we have a space, and any vector is a point in a space, and if we use a dense layer or if we use a neural network, that space is an embedding space that has similar points closer together. So yeah, let's clear this up a bit. Now, if we use the correct loss function here, we should be able to get what we want. If we applied Bob into the network, we get his feature, and then we get to this vector over here, and then we do some transformation from one space to another. Now Bob is now a point in a space. Let's just create a new space here. Don't worry about the flow, it's just random. So this space, Bob is somewhere in here. And another picture of Bob is going to be somewhere in here because the model hasn't learned yet, right? Because, yeah, it hasn't learned yet. And usually when you take a picture of yourself in the phone to do facial recognition is that they require multiple picture from multiple angle. So each of those picture is a point in this space. But it hasn't learned that this is the same space, same face yet. So it just throw it at a random point. Now, if there is a picture of Alice, it's got to be somewhere here, right? It doesn't really matter at all. The distance is all very different. We don't really know. So, in order to train this, what is the target? You know, the loss function for this, it requires a target value. But we don't have a target. What does the target looks like? I'm going to take a moment on this real quick. I might be going a bit too fast. So, the target, the output is in the form of a vector that has any size. So it could be 64, something else. So what is the targets look like? Usually we have a similar size of target, but what is the target? What tell that this output need to be something? What is the correct answer of this output? We don't really know because this vector is not a probability anymore. If it is a probability and we know that this is a Bob picture, we can enforce it to be high to push the probability of Bob to be higher than anything else rather than Alice to be low. But we don't know that. We do know it is Bob, but we don't have a vector. We don't have a target vector at all. And even the output itself doesn't represent probability. That is the problem. So since we stop representing this as a probability, but rather a point in space, we need a different way of training this. And that way is pretty simple. It's called triplet learning. The idea is, let's just say 2 Bob for now. You have 2 points of Bob. And this point is a picture of Bob 1. His first picture, and this is his second picture from the side or something, right? 1, 2. So if this 2 picture is the same a picture of a guy, that means ideally the distance should be small. Basically mean that this point need to be as close as possible together. The ideal situation is that these 2 points stay on top of each other. So both Bob 1 and 2 will be the same. But you know, sometimes it doesn't usually happen that way. There's always something different about the image, and the extraction will prevent it from overlapping. But the point is, the distance between these two should be as small as possible. And if we want to represent the idea of a loss, the larger it is, the terrible it is doing. The terrible the model is doing. So that is our loss function. Let me know if this is a bit too fast and if you have any question.
No, yeah, that makes sense.
That makes sense. Okay.
Mm.
So yeah, the distance between these two need to be as small as possible. So that means if it is large, the loss is also larger. So it is proportional, right, is positive distance between Bob 1 and Bob 2. Now, this is only training on the same phase. It just look at phase number 1 and phase number 2 and try to enforce that 2 phase. But um, we could also try to enforce it so that when it look at a different phase, it could try to bring that phase, try to push that point away from this 2 phase. So that is triplet. You have the anchor, the phase you want to identify, and you have the positive, which is the same types of phase on a different image, and the negative, a different types of phase. So the distance of a negative, let's call it dn, need to be as further as possible, right? Let's remove this third point. So that is what's happening. We want the point of the positive and the anchor need to be closer together, and we want the point of the negative between the anchor and the negative to be as further as possible. We want it to be far apart. So this way, it's learned to push similar phase together and push different phase away from each other. So it's depend, as we discussed, it's depend on how we calculate the loss. And if we use the loss right, the model will learn in such a way to transform the space properly. So hopefully this output is an embedding space that represent phase properly. So this is triplet learning, and the formula is, let's say we have Bob 1, Bob 2, and we have Alice somehow. We need 3 different points, and the distance between each of those has to be the following. The distance between, what am I doing? Yeah, what am I doing? Let's clear that up. The distance between the anchor and the positive, right, need to be as closer as possible, which means if it is high, the loss will be high, and the distance between the anchor itself and the negative need to be as further as possible. So if this is high, we want the loss to be low because it is good for this 2 points to be away from each other. So we put a negative point, a negative sign in front of it. So essentially what it means is you subtract. I think this is the formula, I don't really know exactly. Let's search up triplet learning. Constructive learning. Let's see what is, if anybody have any formula for this. I have no idea what that is. We're not reading paper today. Let's look at picture. Okay, only diagram, but formula, there might be something a bit more complicated. PyTorch triplet learning. So PyTorch, okay, PyTorch has a loss function that does this for us. So we create a loss function, just like cross entropy or anything we want. And when we call it, we give it the anchor, the positive, and the negative point. And it's just distance, yeah, the distance positive minus the negative distance plus some margin. That might be a good thing we could put in. And maximum between 0. So all of this, if it has become negative, we just max it out at 0. Or at least is for this function specifically. Any question about this?
No.
No? Alright.
No.
It's alright, let's take it in slowly. So, right, we went through a lot of things, so it's not a surprise if you cannot take it in all at once yet. It takes a bit of time. So to summarize, we have all of this convolution in between to get some vector, and the convolution is not really necessary. It's just a good thing to extract features. If we use a dense layer from the beginning to the end, that would work too. It's just we gonna have the same problem as before, as we discussed. The curse of dimensionality. A lot of training, a trainable parameter that take a lot of time to train, but also it's not localized and everything. But the point is we want a vector point, a point in a vector space or embedding space, as in the ideal case. And for each of those, right, that is our model. Now to train that, we take two different faces. One of them has two images. So we have the anchor, the face that we're trying to train on. Not train on, but could be any face, as long as we have its positive version, which is another face, another same face in a different image. And we have a negative version of it, so it could be any other face for this one, or maybe a similar one to enforce the model to learn even better, as long as it is different, right? For us, we know it is different, so this is a part of the dataset itself. So we look through a dataset, we try to find two faces that is the same and find another one that is different but maybe similar or not. Does not really matter. And then we apply this formula. Now to get that thing in the first place is we apply this face, all of this, through the network. And after that, each of them will give us a point, right? So to look at the flow, we have, let's say, Bob1 again. We have Bob2, and then we have Alice. And each of them going through the model will give us a embedding point. So Bob1 embedding, I'm just writing this out. Bob2 embedding, in other words, it's just a vector. Alice embedding, right? And since each of this is embedding, or in other words, a vector, the distance between them we could calculate by the following formula. So you have two vectors, you have a v1 maybe, and you have v2. Each of them has a component, so x, let's say it is 2D for now, x and y. This is x and y2, x2, y2, and so on. The distance is we use the Pythagorean theorem. If you remember, it's the square root of x. I don't remember, x2 square in between. You add the y1 minus y2. So it's basically the difference between this square or something. I don't really know. But yeah. So this is a Euclidean distance. I cannot spell that, so I will not try to spell it. Got this part? All of this are just point in space, and using basic geometry, you can calculate its distance. And that distance can be used to find the loss, and as long as we have a loss function, we can call back propagation to train our model. That's the cool part. Now just a bit of different, just a side note, the embedding space can be either based on distance, just like what we have here, or it could be based on an angle from the origin. So we have the Euclidean distance, the Pythagorean theorem. I cannot spell this. And we have another way of calculating sort of a distance on its own, which is to use cosine similarity. Cosine sim, which is not really ideal for this scenario, but it is used in other area, like most likely language processing, for embedding a language, a bunch of words. So embedding space in this case represent points of faces in a space, but in LLM or uh, one of those GPT thing, an embedding space is used to represent words. So similar word will stay close together. But get back to cosine similarity is instead of distant, we have similar space, but point that has similar meaning will have a smaller angle from the origin compared to each other. And point that is very different should be further from the other point in the angle, in the sense of angle. So if you apply cosine similarity, basically apply calculating the angle between this. So that is cosine similarity somehow. Is you do the same thing, but instead of distance you use this formula. And when you apply the loss function and backpropagation and training, the point will naturally form into this form. This is not a good image. Let's remove it. Alright, so that is embedding. Essentially all of it, I think. Maybe not, but that's that. So we have this, and then we have this negative. Any question?
No.
No? Alright. We have 30 minutes. I don't really want to get into coding because the data set for this is terrible. Let's see. Facial recognition. Take a lot of time to read this. So there's a competition on Kaggle. Give you two faces and you tell it whether this two face is different or not, or similar. And there are a lot of faces. So we don't really know the number of faces at all, but we do have a way of calculating the difference no matter what. As long as we have two same face and one different, we can go through all of them and do each one as its own class or loss function. So the way we usually approach this problem, if we want to train our own facial recognition, right? There's existed better one out there already. We don't really have to do anything. But if we were to do this, we use transfer learning. We stop training everything from scratch at this point. Is that the first part, the part of feature extraction that we've been talking about, is we use something like a existed model, which is ResNet, or maybe the VGG. I don't know what that stands for. There's a lot of existed convolution model out there, and we use it. They all usually have the CNN from the beginning, and they have the fully connected layer at the end, and we usually cut it off directly at that point, or maybe a bit closer to the beginning, so that we get lower level ideas rather than try to get some extra abstraction. That is experiment. We need to cut them and test them out, cut them and test them out. And after that, after we cut, we put our own dense layer in here. So it's either a single layer, or maybe you could apply another layer in between to get the actual dense layer at the end. I'm not sure about the activation function in this case, because we want the point to be freely moving throughout the space. We don't want it to be clamped. We don't want to cut it above zero or anything. So maybe at this point we don't usually apply any activation function, but you could apply some at this point. You could apply ReLU or anything else if you need to. But usually at the end we just keep it raw. We keep the transformation linear without having any restriction. That's what my interpretation, but maybe there's a different thing we can do. So we have the dense layer, then we have the embedding, and that's it. And to use this model to train, we already know how to train, is to use triplet learning. To use it is, I haven't go through this, let's see. You ask the user to take a bunch of pictures of themselves. Let's say the model already trained, right? And we have a bunch of points. So each of this picture is applied through the model, and we will get embedding points, a bunch of them. I cannot count. A bunch of them in the embedding space, and that's it. You store this in a vector database or some sort of or you could store it in the memory if you want to, but the point is these are a bunch of vectors, a bunch of points. Now when the user trying to scan their face, right, we have a new face coming in. We don't really know what this face is look like, who face this is. What we do is we apply through the model again, the same model that we already trained, and we get a new point in this space. So let's use the same space, and the point is somewhere here. So you go through all of your existed point, try to calculate the average maybe, right? So this is a clustering problem. Now the new point, the distance between the average or maybe one of this to the new point, if it is closer than a threshold, so if it is shorter than a threshold that you can set, cannot even spell threshold. If it is closer, this point belong to this guy, this class, right? So that is how it usually works. Now, this is just for a phone that belong to a single person, but it doesn't stop us from collecting a bunch of other faces. So this is civilian, civilian, surveillance. So you're collecting a bunch of people, pictures and all that. So this is what China doing. I don't know. I might get kidnapped. But yeah, you get a lot of those points. You was about to say something? Two
Were
faces.
you trying to say civilians?
Surveillance, yeah.
Okay.
Yeah, yeah. Yeah, my English. So we have two face, maybe more, right? All we have to do is to get its embedding for each of those. So it will all stay in the same space. And then when a new points come in, you just need to calculate its distance between this point with every other point and see which one is the closest and what class it is belong to or which person it is belong to, the closest one. So that is how we do it. So we essentially modified our things in such a way with some insight from mathematics of how points are in this space. Hold on, let me. In such a way that we can use it later without having to worry about the types of class it's going to be. Whether there's a 2 person, 5, 10, or a million, doesn't really matter. The model is a meta learning model. It learned to learn about faces in a way. So it's something called one-shot learning, I think. Maybe not exactly. Few shot learning might be fit. So after you train the model just need to look at the picture of a face a few times and it understand what that face is about. And that is enough. You don't have to retrain again and again. I think I forgot to mention a very important point about using a fixed number of class here is that if you have dog, cats, and bird, and you want to put another class in, like a otter or some other animal in there, you have to retrain your whole dense layer. You don't necessarily have to retrain this because it's already worked by one of this model. What did I just do? You already took, brother. What's happened? You already took the feature extraction from one of the model, but this thing is the one that doing the classification, right? So we have to retrain it again and again if we increase the vector bit by bit, or if we increase it 3 class at a time, we still have to retrain it. Did I hear something? Okay. So that retraining also requires dataset, but we don't do that. I don't know if we could do this for even just image for the previous problem. So we could do this for a bunch of faces, right? And all faces have similar things. They all have eyes, they have nose. So each of these layer extract those feature. But at the end, each of these represent a characteristic, categories, cannot speak, characteristic of a nose or of both eye. Each of this point represent how is the eyelash, how is the eyebrows, and so on. And the closer the eyebrows, the point may be closer on one axis. And if the nose and mouth and everything are similar, then also the point will be closer based on that. So that is another intuition that you can think of. The embedding is essentially representing features of a bunch of faces. So it could be any face. So the question is, could we use this to identify different animal without having to set a fixed size of classes? So let's say we've set it to 64 and train it on different types of animal. Now we introduce a new types of animal comes in, a different class, entirely different class. Can it do that, or it has to be the same types of animal with different breed, like a dog, but with different breed? So that is a good question to get into later, but we don't really know. We have to test it out. Maybe there's someone's already done that. But yeah, we just went through the entire thing about this. Um, that's it. That is it. Any question, comments, concern?
It seems interesting, but I think I'll have to go over it again.
Yeah. Okay. Hold
Yeah.
on. Let me see if I record it. Okay. It is recorded. Paranoia. So I think this is it for convolution. There might be other ideas that we could get into, but
We're not gonna go through that data set
I don't think we have enough time today. So we could go through it next time.
next time. Yeah, sure.
Yeah. Maybe we could even. How about you try it first, and then when we come
Mhm.
together, we can see if we have any problem, and then we can talk about it rather
Okay.
than me going through this.
Yeah,
So
that makes sense. I'll try it out.
so this might be a bit tough.
Uh
So
huh.
just let me know if you have any problem, but it's gonna
Okay.
be a
Sure.
good practice.
Okay.
We can end it early. One thing we could do later after the data set, we could go through RNN, which is another architecture. We try not to go too deep into one specific field. We're just gonna go roughly around it so that we understand how the whole thing actually worked, how we have the power to modify all of this just to get it to work the way we want it to, right? We've seen it before. We modified the convolution in such a way that it extract image feature. Now, how do we work on a sequence of data. You have text, and those texts is not fixed. It could be any size, right? How do we feed that into neural networks? So that is another question. We could get into transformer, which is the most important, not important, but the most popular thing everyone is using right now for the chat GPTs and everything. That's what we could do. That's it. Any suggestion?
Um, for the content, I just feel like we should go with what you feel is right.
Okay.
But let's try announcing it first. Like, remember, I think last week or the week before that,
Yeah.
Karina made an announcement, and then I think we had a pretty okay turn up.
Mm.
Maybe people just forgot about the meeting, so maybe we can
Yeah.
like make a weekly announcement on Monday
Yeah.
evening or
Yeah.
something.
We could do that. I did do it.
But
Or let me stop recording.
last week, right?